This is Chapter 1. This is Part D, the lecture on homeostasis. And this information is in your textbook starting on page 8. And we're going to cover the importance of homeostasis as it is one of the most central themes that's important to anatomy and physiology. And as you can see from this tightrope walker, he is struggling with maintaining homeostasis at this point. It's a state of balance in the body, and we use the term when we describe it dynamic equilibrium. And dynamic equilibrium means that things are constantly in flux. So the word dynamic means changing, and equilibrium means state of balance. And in our body, there are many, many variables that are constantly changing, and our body is responsible for monitoring all of these many changes. And it monitors all of these variables, and as it does so, it then responds accordingly so that we can maintain homeostasis. And there are many, many different examples. At the beginning of this lecture, I'm going to introduce this concept and give you some examples from everyday life that you're already quite familiar with. So homeostasis is the maintenance of a relatively stable internal condition despite many changes that may and will occur all throughout a 24-hour period. So it's maintained by all of our organ systems. The two main systems, though, that we're going to focus on for this are the nervous and the endocrine systems. And these are the controlling systems that we have. Remember, the nervous system works very, very quickly. The endocrine system takes a longer period of time. But if we think back to what goes on in everyday life, we set our home temperature possibly at maybe 74 degrees, and 74 degrees Fahrenheit would be the state of balance that we set our internal house temperature at. But when things get too warm, then the fan is going to turn on. When it gets too cold, the heater is going to turn on. This is exactly what happens in our body in order to maintain heat control, which in our body we refer to that as thermoregulation. So our body needs to work to maintain a constant body temperature of about 98.6 degrees Fahrenheit. So this means when our body temperature goes above 98.6 degrees Fahrenheit, this means that there are going to be mechanisms that automatically kick in to make sure that our body cools down. So usually this is something that happens in the brain. The brain is going to do something to sense the increase in body temperature. The brain will trigger some sort of pathway so that we are able to cool down through a cooling mechanism, which is usually sweating, for example. And if the temperature goes up, let's say, to 99 degrees Fahrenheit, which is very extreme, there will be something that happens to cool our body temperature so that it returns back down to 98.6 degrees Fahrenheit. This would be an example of maintaining homeostasis. So maintaining homeostatic control. So let's examine the major parts of a homeostatic control mechanism. You have the same figure in your book on page 9. It's figure 1.4. And you can see that there is this seesaw that's constantly going back and forth. And this is quite normal depending on what the stimulus is going to be. So part 1 of this pathway, the stimulus, is going to be the variable that produces the change. So the heat, for example, could affect the variable, could change the variable. And the stimulus is going to be detected by the second part of this pathway called the receptor. So the receptor detects the stimulus and it sends input into usually the nervous system. So the input, in this case the information, is going to travel along the afferent pathway. And the word afferent means towards. So keep in mind here, I'm going to underline the TO part, that there is a signal that is traveling towards the control center. And quite often the control center is going to be the brain. There are other examples in the body, but we're going to use the example of the brain as we start off with this discussion. So there's an afferent pathway. There's also an efferent pathway. The efferent pathway is going to travel out the output pathway. And so in this case, the info travels along the efferent pathway. Think of the word efferent kind of like effect, and it is the pathway that goes away from the control center. So we have the efferent pathway, which is traveling via the travels to the effector, and the effector is what eventually is going to produce the response. And the response is used to help our bodies return back to homeostatic balance. So these are the main 5 parts that you need to be aware of for the homeostatic control mechanism. The set point is what is determined by the control center, by the brain. So it is responsible for helping to ensure that variables, and we're going to say, for example, here a variable would be something like blood pressure, that variables remain within a set point range. And an example of this is normal blood pressure would be 120/80. However, our blood pressure goes up and down all throughout the day, every single second, and the body wants to wants to ensure that the blood pressure probably stays between maybe 100/90 to 130/100. Actually, not 100/80, 100/70, up to 130/100. But there's this specific set range that the control center helps to ensure that these homeostatic variables remain within a certain range. Our next slide is showing the same figure that you have on page 10. It's figure 1.5. And in this case, we can fill in the boxes here. We have our receptor. We have our control center. We have our effector. So these are the 3 main parts of the homeostatic control pathway, but as you saw on the previous slide, we also have the stimulus and the response that you should be aware of. When you're trying to figure out what type of feedback loop this is, you want to pay particular attention to the direction of the stimulus, which is number 1 in our homeostatic control pathway, and you also want to pay attention to number 5, which is the response. And pay special attention to the direction of the stimulus versus the response. So if we look at this top pathway, we can see that the body temperature goes up. So the stimulus is an increase in body temperature. So the receptor is going to detect this. It's going to send information via the afferent pathway, which is where the input will travel to the control center. The control center then will send the output via the efferent pathway to an effector. So the response is going to be that there are sweat glands activated, and the eventual response is that there is a decrease in body temperature. And because the stimulus and the response are in opposite directions, we know that it is negative feedback pathway. So again, pay attention to the stimulus, and because there is an increase in temperature and a decrease in temperature for the response, the only important thing to remember is since they are in opposite directions, this means that it is negative feedback pathway. So negative doesn't necessarily mean that it's good or bad. It just refers to the direction of the stimulus versus the response. So that's the take-home message from this lecture, is that the stimulus is going to be opposite of the response for a negative feedback pathway. If we look at the bottom of this figure, we also have our major steps here. We have our receptor here. The receptor is also going to detect temperature levels. That takes the input to the control center. And then we also have the effector in this case. So in this case, the stimulus is going to sense a decrease in body temperature. That sends a signal from the receptor to the control center, which is the input. Then there is going to be output that travels back to the effector, and that output is going to activate skeletal muscles to cause shivering. It might the person may decide to put on a coat to warm up, but the end result is that there is now an increase in temperature, which now is going to allow this person to return to homeostasis. So again, since they're in opposite directions, we have a decrease in temperature right here, and there's an increase in temperature here. As long as the stimulus and the response are in opposite directions, we know that it's negative feedback. So if we look on our next slide here, the important information that I want you to pay attention to is that in a negative feedback pathway, the response is going to reduce or shut off the original stimulus. So they're in opposite directions. Opposite is your key term here. So our example of regulation of body temperature is an example of negative feedback because the response is opposite of the stimulus. Another example would be what happens with blood volume, and this is controlled by the endocrine system, one of the other control systems that we have in our body. But ADH is a new term. You're going to learn about this in anatomy and physiology too. But ADH stands for antidiuretic hormone. And so what this hormone does is it prevents water loss, prevents diuresis. So if somebody has very low blood pressure, this would be the stimulus. The endocrine system would detect this, which is our control center. And so the endocrine system wants to do something to increase blood pressure, to return blood pressure to where it should be. And so one way that it can do this is to release ADH. And so ADH is going to prevent fluid loss. And if it prevents fluid loss, this will end up increasing blood pressure. But you can see since the stimulus again is going to be opposite of the response, we can see that it's going to be negative feedback as well. And the large majority of the time, about 98%, maybe a little more or maybe a little less than this, but about 98% of feedback mechanisms are negative. About 98% of them are negative. The opposite then would be positive feedback. And these are rare occurrences. So there are positive feedback mechanisms in the body, but they are very, very rare. And you can see the key here is that the responses are going to enhance or exaggerate the original stimulus. So for example, if there's an increase in body temperature and the response of the body is to increase body temperature even more, that would be considered a positive feedback system. So the response is in the same direction as the stimulus. And it could amplify or lead to a cascading effect. Many times, if there's a positive feedback system, this means that there could be a disease present. So it could be, and not all the time, but it could be the sign of a pathology. And remember from earlier in chapter 1, pathology means disease. So it could be a sign of disease, but not always. There are normal positive feedback systems. For example, the enhancement of labor contractions by oxytocin. Oxytocin is a positive, works via a positive feedback mechanism, but oxytocin and pitocin is actually a synthetic oxytocin. So when they induce labor, they're using pitocin. Oxytocin is a hormone that also it causes the uterus to continue to contract. So it causes the uterine smooth muscle to contract. So if we think about the parts of the feedback pathway, the stimulus is that there are uterine contractions. This sends a signal to the brain. So it sends a signal to the control center. And the response is going to be that there is an increase in uterine contractions as well. So again, I want you to focus on the stimulus and the response. So as long as the stimulus and the response are going to be in the same direction, it's going to be positive feedback. Platelet plug formation and blood clotting are other examples, and we'll look at those on the figure on your next slide here. And this is the same as you have figure 1.6. So number one, in this case, at the top of your screen is going to be the stimulus. The first thing that happens is there is a break or a tear in the blood vessel wall. So this is going to be the stimulus that then sends a signal to the control center. There's going to be platelets that are released. And so this is sort of the initial event that happens. Platelets are going to be released. So this is thought of as the stimulus. There's going to be what's called a platelet plug that happens. But the end result is that there are more platelets that are released. And so since the stimulus and the response are exactly in the same direction, it's going to be positive feedback. So again, this is going to be the stimulus here. Platelets are released, and more platelets continue to be released as the response. So the key here is that the stimulus is the same as the response. So that's really all you need to remember to identify it as positive feedback or negative feedback. Again, the large majority of the time it's going to be negative feedback, but there are some rare instances where it is positive feedback. And so many disturbances of homeostasis, and remember the word disease means pathology. So if there is a disturbance of homeostasis, it could be a sign of pathology. In this case, the control center, or the control systems, could start to weaken and kind of weaken with age. A really good example of this is when somebody starts to develop heart failure. And many of you, I'm sure, have heard of the term heart failure. You may have heard the term CHF, which stands for congestive heart failure. It's very unfortunate when this starts to happen as we age, but what's going to happen is let's say, for example, that the blood pressure is too high. So there's high blood pressure. This is going to act as the stimulus. So normally what should happen is there's going to be an afferent pathway that goes to the control center, which in this case is the heart. The heart is going to be able to sense that there's high blood pressure. It's going to send a signal away from the heart to reduce the amount of blood pressure, and so that normally would be the response. However, if the control center is starting to weaken here, if this is the problem, the heart is going to no longer be able to respond accordingly. So instead of a decrease in blood pressure, there tends to be a further increase in blood pressure. So we know just from that that since the stimulus is the same as the response, that it's going to be a positive feedback system. And that will include the end of this mini lecture. And the next mini lecture is the rest of Chapter 1, and it's going to be on the language of anatomy.